Hello and welcome to today's session. Today, we're diving into a fascinating technique called Kadan's algorithm, which helps us solve a specific problem with arrays in a clever and efficient way. If the name sounds intimidating, don't worry. It's actually a simple idea that we'll break down together step by step. Kadan's algorithm is designed to find a continuous piece of an array, called a subarray, where the numbers add up to the largest possible total. Imagine a list of numbers, some positive like 4 or 10, and some negative like -2 or -5, representing something like daily profits or losses. Kadan's algorithm identifies the best consecutive chunk of this list that gives the highest sum when added together. We'll use a real-life analogy to make it relatable, walk through a detailed example with a visualizer, and explore why this algorithm is so fast and efficient. By the end, you'll feel confident using Kadan's algorithm to tackle this problem. Let's get started. Introducing Kadan's algorithm and subarrays. Kadan's algorithm is all about finding the maximum sum of a subarray within a given array of numbers. A subarray is simply a group of numbers that are next to each other in the list, like a continuous slice of the array. For example, in the array 1, 4, 2, 10, 2, 3, 1, 0, 20, 5, 8, 12, one subarray could be 4, 2, 10, which are the numbers at positions 1 to 3, or another could be 20, 5, 8, from positions 8 to 10. The goal is to find the subarray where the sum of its numbers is the largest possible. What makes Kadan's algorithm special is its speed. Instead of checking every possible subarray, which would take a long time, it scans through the array just once, making smart decisions at each step to keep track of the best sum. This efficiency is like finding a shortcut to solve a puzzle without trying every combination. To make this concept come alive, let's use a real-world analogy that you can picture easily. Real-world analogy, the treasure hunt. Imagine you're a treasure hunter walking along a path in a forest. Each step you take has a treasure chest, but some chests contain gold coins, positive numbers, while others have debts you must pay, negative numbers. For example, one step might give you 4 coins, while another makes you lose 2 coins. Your goal is to find a continuous stretch of the path, a sequence of steps without gaps, where you collect the most gold overall after paying any debts. As you walk, you face a decision at each step. Should you continue the path you're on, adding the current step's coins or debts to your total, or should you start a new path from this step because the previous path has too many debts? You also keep a mental note of the best stretch of the path you've found so far, the one with the most gold. Kadan's algorithm is like this clever treasure hunter, making these choices at each step to maximize the total gold while remembering the best path discovered. This analogy will guide us as we learn how the algorithm works. The problem Kadan's algorithm solves. Kadan's algorithm is designed for a problem called the maximum subarray sum problem. You're given an array of numbers, which can be positive or negative, like 1, 4, 2, 10, 2, 3, 1, 0, 20, 5, 8, 12. Your task is to find a subarray, a continuous sequence of numbers, that has the largest sum when you add them up. For example, in this array, one subarray might be 2, 10, 2, which adds to 2 plus 10 plus 2 equals 14. But there could be another subarray with an even larger sum. This problem is exciting because it's like identifying the best part of a sequence, such as the most profitable streak of days for a business or the highest scoring segment of a game. The challenge comes from negative numbers, which can reduce the sum, forcing you to decide whether to include them or look for a different subarray. Since the subarray must be continuous, you can't skip numbers in the middle, making the problem tricky but interesting. Negative numbers are particularly important because they can drag down the total, requiring you to weigh whether extending a subarray with a negative number is worth it or if starting fresh is better. Kadan's algorithm handles this by cleverly balancing these choices as it moves through the array. Beginner-friendly example to build intuition. To get a feel for the problem, let's explore our array. 1, 4, 2, 10, 2, 3, 1, 0, 20, 5, 8, 12. This array has 12 numbers, and our goal is to find the subarray with the largest sum. Let's think about what this means by considering a few possible subarrays to build intuition. One subarray could be the first three numbers, 1, 4, 2, which adds to 1 plus 4 plus 2 equals 7. Another could be 10, 2, 3, which is 10 plus 2 plus 3 equals 15. Or maybe the last four numbers, 20, 5, 8, 12, which add to 20 plus 5 plus 8 plus 12 equals 45. There's also the entire array, all 12 numbers, which we'll calculate later, but it includes both positive numbers like 20 and smaller or negative numbers that might reduce the sum. Listing all possible subarrays would be overwhelming because, for 12 numbers, there are many combinations of consecutive numbers. For example, you could have 4 alone, 4 and 2, 4, 2, and 10, and so on. Checking each one by adding its numbers would take a long time, especially for larger arrays. Kadan's algorithm avoids this by making decisions as it scans the array, finding the maximum sum without testing every possibility. This example helps us see the challenge. We need to balance positive numbers that increase the sum with negative or small numbers that might decrease it, all while keeping the subarray continuous. Kadan's algorithm is like a guide that knows when to extend a path or start a new one to maximize the treasure. How Kadan's algorithm works. Now let's dive into the heart of Kadan's algorithm and see how it solves the maximum subarray sum problem. The algorithm is surprisingly simple. It walks through the array one number at a time, keeping track of two important values. The first value, called the current maximum, is the largest sum possible for a subarray that ends at the number we're currently looking at. The second value, called the maximum so far, is the largest sum we've found for any subarray throughout the entire process. Here's the step-by-step process. Start with the first number in the array and set both the current maximum and the maximum so far to that number. This assumes that, with only one number, it's the best subarray so far. Then, for each number after that, make a decision. Should you start a new subarray with just the current number or add the current number to the subarray you were building before? To decide, calculate two options, the current number by itself or the previous current maximum plus the current number. Choose whichever is larger and update the current maximum to that value. After updating the current maximum, check if it's larger than the maximum so far. If it is, update the maximum so far to this new value, as you found a better subarray. Continue this process for each number in the array. When you reach the end, the maximum so far will be the largest subarray sum. Let's connect this to our treasure hunt analogy. Each number is a step on the path, and the current maximum is the total gold collected on the path ending at the current step. At each step, you decide, do you start a new path with just this step's coins, or add this step's coins to the previous path's total? The maximum so far is the most gold you've collected on any stretch of the path. You update your notebook at each step to track the best treasure found. To formalize this, here's a simple recipe for the algorithm, like a set of instructions for our treasure hunter. Initialize the maximum so far and the current maximum to the first number in the array. For each number starting from the second one, update the current maximum to the larger of the current number alone or the previous current maximum plus the current number. Then, update the maximum so far to the larger of the current maximum or the existing maximum so far. At the end, the maximum so far is the answer. This process ensures that you always know the best subarray sum up to each point and the overall best sum, all in one pass through the array. Detailed example with dry run. Let's apply Kadan's algorithm to our array. 1, 4, 2, 10, 2, 3, 1, 0, 20, 5, 8, 12. The problem is to find the contiguous subarray with the largest possible sum and return that sum. We'll walk through each step, tracking the current maximum and maximum so far. Imagine a row of 12 boxes representing the array 1, 4, 2, 10, 2, 3, 1, 0, 20, 5, 8, 12, labeled with indices from 0 to 11. There are also two displays, one for the current maximum and one for the maximum so far. Start with the first number at index 0, which is 1. Since it's the only number so far, set the current maximum to 1, as the best subarray ending at index 0 is just 1. Set the maximum so far to 1, as it's the best sum overall. Move to the second number at index 1, which is 4. Adding to the previous current maximum gives 1 plus 4 equals 5. Since 5 is larger than 4, update the current maximum to 5, meaning the best subarray ending at index 1 is 1, 4. Compare the current maximum, 5, to the maximum so far, 1. Since 5 is larger, update the maximum so far to 5, and note this subarray spans indices 0 to 1. Next, go to index 2, value 2. Add to the previous current maximum, 5 plus 2 equals 7. Since 7 is larger, set the current maximum to 7 for the subarray 1, 4, 2. Compared to the maximum so far, 5. Since 7 is larger, update the maximum so far to 7 from indices 0 to 2. At index 3, the number is 10. Add to the current maximum, 7 plus 10 equals 17. Since 17 is larger, set the current maximum to 17 for 1, 4, 2, 10. Compare to the maximum so far, 7. Update the maximum so far to 17 from indices 0 to 3. At index 4, value 2. Add 17 plus 2 equals 19. Set the current maximum to 19 for 1, 4, 2, 10, 2. Compare to the maximum so far, 17. Update to 19 from indices 0 to 4. At index 5, value 3. Add 19 plus 3 equals 22. Set the current maximum to 22 for 1, 4, 2, 10, 2, 3. Update the maximum so far from 19 to 22 from indices 0 to 5. At index 6, value 1. Add 22 plus 1 equals 23. Set the current maximum to 23 for 1, 4, 2, 10, 2, 3, 1. Update the maximum so far from 22 to 23 from indices 0 to 6. At index 7, value 0. Add 23 plus 0 equals 23. Since they're equal, keep the subarray, so the current maximum stays 23 for 1, 4, 2, 10, 2, 3, 1, 0. The maximum so far remains 23. At index 8, value 20. Add 23 plus 20 equals 43. Set the current maximum to 43 for 1, 4, 2, 10, 2, 3, 1, 0, 20. Update the maximum so far from 23 to 43 from indices 0 to 8. At index 9, value 5. Add 43 plus 5 equals 48. Set the current maximum to 48 for 1, 4, 2, 10, 2, 3, 1, 0, 25. Update the maximum so far to 48 from indices 0 to 9. At index 10, value 8. Add 48 plus 8 equals 56. Set the current maximum to 56 for 1, 4, 2, 10, 2, 3, 1, 0, 25, 8. Update the maximum so far to 56 from indices 0 to 10. At index 11, value 12. Add 56 plus 12 equals 68. Set the current maximum to 68 for the entire array. 1, 4, 2, 10, 2, 3, 1, 0, 25, 8, 12. Update the maximum so far to 68 from indices 0 to 11. After processing all numbers, the maximum subarray sum is 68, and the subarray is the entire array. Indices 0 to 11. 1, 4, 2, 10, 2, 3, 1, 0, 25, 8, 12. This dry run shows how Kadan's algorithm builds the solution step by step, always choosing the best subarray ending at each position and updating the overall best sum. Time and space complexity. Let's explore why Kadan's algorithm is so efficient by examining its time and space complexity, which tell us how fast it runs and how much memory it uses. For time complexity, the algorithm is remarkably fast because it processes each number in the array exactly once. For an array with n numbers, it performs a few simple operations at each step, comparing the current number to the sum of the previous current maximum plus the current number, and updating the maximum so far if needed. These operations take the same amount of time regardless of the array size, so the total time is proportional to n. In efficiency terms, This is O of n time, meaning if you have 100 numbers, you do about 100 steps, or for 1,000 numbers, about 1,000 steps. Compare this to a naive approach that checks every possible subarray. For n numbers, there are about n squared subarrays, since each subarray has a start and end position, and adding the numbers in each could take up to n steps, leading to O of n cubed time. For n equals 100, that's 1,000,000 steps, versus 100 for Kadan's algorithm. Kadan's is like walking straight through the treasure path, while the naive approach tries every possible route, wasting time. For space complexity, Kadan's algorithm is extremely efficient. It only needs two variables, the current maximum and the maximum so far, regardless of how large the array is. These variables store single numbers, so the memory used doesn't grow within. This is called O of one space, or constant space, meaning it's as memory efficient as possible. In our treasure hunt analogy, it's like the hunter needing only a small notebook to track the current path's gold and the best treasure found, no matter how long the path is. This combination of O of n time and O of one space makes Kadan's algorithm ideal for large arrays, as it's both fast and lightweight. When to use Kadan's algorithm? Kadan's algorithm is perfect for finding the maximum sum of a contiguous subarray in an array of numbers, especially when the array includes both positive and negative numbers. It's used in problems like identifying the most profitable sequence of days for a business, the highest scoring segment in a game, or the best range of data in signal processing. It's also a foundation for more complex problems, like finding maximum sums with constraints or extending to two-dimensional arrays. You'll encounter it in challenges where efficiency is key, and the subarray must be continuous, making Kadan's algorithm a go-to solution for optimizing performance. Common mistakes to avoid. When using Kadan's algorithm, watch out for a few common pitfalls. First, ensure you update the current maximum correctly by comparing the current number to the sum of the previous current maximum plus the current number. Forgetting to consider starting a new subarray can lead to incorrect sums, especially with negative numbers. Second, handle edge cases, like an array with all negative numbers. Kadan's algorithm still works, picking the largest single number as the maximum sum, but you should verify this in your solution. Third, don't confuse the current maximum with the maximum so far. The current maximum is only for subarrays ending at the current position, while the maximum so far tracks the overall best sum. Mixing them up can cause errors in tracking the maximum sum. Finally, remember that Kadan's algorithm assumes the array has at least one number and returns a non-empty subarray sum. If the problem allows an empty subarray with a sum of 0, you'll need a slight modification, though this is rare. You've now mastered Kadan's algorithm. It's like a treasure hunter finding the best stretch of a path with the most gold in a single, efficient journey. We explored how it solves the maximum subarray sum problem by scanning the array 1, 4, 2, 10, 2, 3, 1, 0, 20, 5, 8, 12, keeping track of the current maximum and maximum so far, and found the maximum sum of 68 for the entire array. The visualizer showed how it builds the solution step by step, highlighting each number and marking the final subarray. We also learned it's incredibly efficient, with O of n time and O of one space, making it far faster than checking all subarrays, which takes O of n cubed time. This algorithm is a powerful tool for finding the best continuous sequence in an array, and you can practice it with different arrays or explore related problems to deepen your understanding. Keep experimenting, and you'll find Kadan's algorithm becomes second nature. Thank you for joining me today, and I look forward to diving into more problem-solving adventures in our next session.